Hello class, welcome to Chemistry Today. In this video, we're going to take a close look at chemical reactions and review balancing. So let's jump right into it. There are some videos on Schoology that run through a couple different chemical reactions, anywhere from explosions to color changes, some things that we might not even be able to do in our laboratory. Take a look at those. They give you kind of an idea what we're talking about. But basically, at the end of the day, what we're going to be using a lot is a model for what a chemical reaction is in our lab, or maybe some models about things that we might be reading or discovering about. That model follows this template where we have an equation that is describing what is happening in the chemical reaction. Okay, what makes up this? Well, we have two sides of the equation. We have the side on the left that are the elements and compounds that are reacting together. We call them the reactants. And we have the side on the right that is being produced as a result of that rearrangement of atoms. They are called the products. Okay, so when we look at our chemical equation, you're going to see reactants on the left side and products on the right side, and you're going to see an arrow that indicates that some sort of rearrangement has been going on. That chemical reaction has happened. The other thing to pay attention to in our chemical equation is what state of matter those reactants products might be in. Solid, liquid, and gas might be really obvious to you. The new one might be the AQ. That stands for aqueous, or it's been dissolved in water, or it's still in a solution in that chemical equation. All right, let's jump ahead a little bit to how do we know that chemical reactions are actually happening? There are some clear signs and clear evidence that we can look at. One is a change in color or an odor, like you might smell something different, especially sulfur is a very pungent odor, smells like the rotten eggs. A release of energy, so either heat or light. You can think of a hot pack or even a cold pack. Those are chemical reactions that are happening that change the energy. Production of sound, so you might hear a pop or a fizz. Forming a solid. Now, in chemistry, we give that solid a name. We call it a precipitate, and that might look like a cloudiness in your test tube, or it might look like flakes. Those types of things are formed in a few reactions. Also, temperature change, increase or decrease of a temperature, or the formation of a gas. You can see that bubbling or that fizzing. These are all signs that a chemical reaction is taking place. You're getting a new product after those elements have been and atoms have been rearranged. What does it look like? Well, on the surface, on the macro level, you might see like food decomposing or rotting. That's a chemical change, a chemical reaction. Rust on a car. This is a good example of a precipitate where you see two clear liquids, and when they're mixed together, they form this yellow cloud of solid particles. All right, that's a precipitate. The other thing might be forming a gas, and you can see whatever reaction is happening in this Erlenmeyer flask, the gas is being captured and bubbled up, and it's displacing the water in this other container. All right, or even cooking. Cooking over a fire, like roasting marshmallows, that is actually a chemical change. All right, so we're going to take a look at a lot of those things. We have 5 different types of chemical reactions that we're going to be really paying attention to. I'm going to go into more detail of each of these 5 types in later lessons. Just know that these are the 5 that we're going to be focusing on: synthesis, combining to make a new product; decomposition, breaking things down into smaller products; combustion, that is anything that is burning, is combusting; and then a single replacement and a double replacement. So there are elements that might be able to displace others in a chemical reaction based on how reactive they are. All right, and we're going to take a look at both of those cases as well. The thing that I want to focus on next is when we have an equation, we need to make sure that mass is conserved. Our model must represent the conservation of mass. And to do that, we need to have the same number of atoms on the reactant side and the same number of atoms on the product side. Well, how do we know how many atoms we have? We have to take one step back and looking at our formulas like NaCl or CaCO3 or NH4,2CO3, we have to be able to count how many carbons, nitrogens, hydrogens that we have in each of those chemical formulas. All right, so a little bit of a review. when we're looking at counting atoms, we're going to be paying attention to the small number that is called the subscript that comes after the elements. All right, that's going to tell us how many of those we have in our formula. Notice that the subscript after Na and Cl is absent because it's assumed that there's just one. So I have one sodium atom and I have one chlorine atom in that compound. All right, for calcium carbonate, I'm going to look a little bit closer, and I notice that there is one calcium and one carbon, but the three, that subscript that's after the oxygen, tells me that there are three oxygen atoms. All right, looking at something with parentheses, we're going to distribute the number after the parentheses to everything inside. So kind of like the distributive property in math. So this tells me that there are two nitrogens. Instead of just 4 hydrogen, now I have 4 times 2, so I have 8, 1 carbon, and 3 oxygen. The 2 only counts for the things inside the parentheses. All right, taking another look, we have a subscript after barium, so that's going to tell me that there are 3 bariums. The 2 gets distributed inside the parentheses, so 2 phosphoruses and 8 oxygens. Now, if you need to pause the video at this point and kind of review some of these things, do a couple practices on your own. This is the essential thing to know and understand before we can balance our equations. Okay, welcome back. When we take a look at balancing equations, we're also going to be taking a close look at two different things. One is the subscript that I already talked about, and that, of course, is a small number like the 4, the 2, and the 3 that comes after the element in the chemical formula. And it's only applied to that element, or in the case of a parentheses, only applied to the things inside the parentheses. A coefficient, however, is a number that is in front. In this case, there's a 2 for the coefficient, and it distributes to everything that comes next. So it applies to all of the elements in that compound, much like the distributive property in math. Okay, so coefficients in front, subscripts are next to, or in the lowercase, and they're the subscript font and format that you'll be looking at. Okay, so how does this equate to balancing? Well, remember I mentioned that in order to balance something, we need to have the same number of atoms on both sides of the arrow. So the reactants and the products. We can't create or destroy matter, so we have to account for the conservation of mass by balancing our equations. So without balancing, this would have H2 plus O2. Without balancing, I would have 2 hydrogens on both sides, but I would also have 2 oxygens on the reactant side, but only 1 on the product side. That's a problem. So we're going to add those coefficients like I did here, 2 in front of the H2 and 2 in front of the water, and that will help us balance out. I'm going to count each of the atoms of hydrogen and each of the atoms of oxygen on both sides just to verify and make sure that we have a balanced equation. So remember, this 2 will multiply by the 2 existing hydrogens that are already there. So I have a total of 4 hydrogens on this side. And I just have 2 oxygens from the subscript on this side. All right, so I need to make sure I have 4 hydrogens on the other side and 2 oxygens to make sure that I have a balanced equation. So the coefficient 2 will again multiply by both of these. So 2 times 2 gives me 4 hydrogens. That's awesome. And the 2 also multiplies by the oxygen to give me 2 oxygens. This is a setup that is balanced. Everything is good. So we are done. So by adding the coefficient of 2 and 2, I'm going to now have a correctly balanced equation. All right, you might run across balanced equations that have higher numbers than 2, and that's totally okay. What you want to do, though, is you want to remember to always reduce it. This does end up with the right number of hydrogens and oxygens on both sides. So if I count them right now, I have 12 hydrogens, and I also have 6 times 2, I have 12 oxygens. If I look on the other side, I'm also going to have 6 times 2, 12 hydrogens. That's great. And for the oxygen, it's divided between water and oxygen gas. 6 plus 6 gives me 12, so everything does balance out. However, I need to make sure I have this in the reduced or simplified form. So instead of using a 6 and a 6, I'm going to use a common multiple, okay? So I'm going to do divide everything by 3. So I'm going to get a 2, 2, and a 1. Now let's double check our math and make sure that that still adds up to the same number of hydrogens and oxygens on both sides. Excuse me. So right now I have 4 because 2 distributes here and it's going to distribute here. So I have 4 oxygens and 4 hydrogens. On this side I have 2 times 2. That gives me 4 hydrogens. 2 plus 2 gives me 4 oxygens. So everything balances. Again, you want to make sure it's in the simplest form once you're done. Okay, here's a couple other examples. Let's take a look at this zinc and zinc chloride one, all right, and copper chloride, sorry. Looking carefully, a lot of times the coefficient of a 1 is implied, and we don't need to write it when we're writing out freehand, but if you're doing something digital, you might have to add that in. So if I look carefully, there's 1 zinc on both sides, so I can just put a coefficient of 1 in front of that. That means there's 1 times the 2 chlorines, so there's 2 chlorines. Oh, there's 2 chlorines on the other side, great, and 1 copper. So going back and forth, I balance this by just adding a 1 in front of in front of all the coefficients. All right, awesome. Let's take a look at another one. I'm going to have us take a look at this number 5 here. All right, balancing this out, we have silver nitrate and sodium chloride makes silver chloride and sodium nitrate. All right, remember we have to have the same number on each side. My hint and my tip for you here is if you see a polyatomic on the reactant side and you see that same polyatomic on the product side, keep that group together and count it as a group. So I'm going to count this as 2 nitrates, and I'm going to want to have a adjustment of a coefficient so that I have 2 nitrate groups on this side. Remember, the 2 distributes to the sodium and to everything that follows. So it also counts as 2 nitrate groups. Now I'm going to trace that back. I have 2 sodiums on this side. I'd better put a coefficient of 2 in front of here because that's going to multiply by the sodium and the chlorine. Double check, I have 2 chlorines on both sides because of the subscript here and the coefficient on this side, and 1 silver and 1 silver. So that balances. By taking into account that that polyatomic can stay together, it's a group, and just counting it as a group, it makes the balancing a lot easier. Okay, once again, I see a polyatomic on this one as well, an SO4 here and an SO4 here. I see 2 chlorine on this side, I see 2 chlorine on this side, 1 barium, 1 barium, 1 magnesium, 1 magnesium. This balances just by counting it up and having 1 as a coefficient. All right, here's the thing I'd like you to try is please take a look at the last slide on our notes. Here is the answer key for that last slide. Make sure you understand how to do this balancing and practice a few of the practice assignments in Schoology. Thanks, have a great day.